Welcome back, everyone. So we're talking about horizontal scaling, and we're talking about cloning these web servers. So what does that mean to clone the web server? Well, let's go back to that example where we understood what comprised of a web server. A web server runs some application logic, and it has access to a database. In this particular case, you can see that the application logic lives on the web server. Now, the database typically lives external to the web server as far as we're concerned, because the web server communicates with the database in order to get this data. But let's talk about cloning out your web server. You are going to clone the application logic because the logic runs independent of the server. It doesn't really care what server it's running on. The code stays the same. However, does it make sense to duplicate the data in the database if it's pretty much the same data? Probably not. The database should pretty much just contain all of the data, and then all these different web server copies are all going to connect to the same database, and then the respective application logic will sift through the database data to pull out the appropriate things it needs in order to serve its appropriate function. So this is cloning. You're essentially just duplicating these web servers, most likely virtually, just meaning that you're copy and pasting these web server nodes, which we'll talk about more later. For now, all you need to understand is that they're duplicates of the application logic. And then chances are with a database, they're all just accessing the same database somewhere on the system in order to serve the actual code function that it has to do. So now that we understand, at least at a very high level concept of this cloning as an idea of scaling out the system horizontally, how do we now fit this into this model where we have all of these hundreds, if not thousands or hundreds of thousands of users all trying to still request posts from our web server? How do we horizontally scale out these web servers in order to service all these different users? Well, the answer here is to use a load balancer. But before we even explore a load balancer, we need to understand some of the problems that are going to arise and what load balancers do in order to solve these problems. But also, there's a couple assumptions we need to understand. So here I'm going to move this out like so. Here, what you see on the left is a bunch of different user client browsers. So on the left, I've split it up like this so that you can see it as a really large number of them. On the right-hand side, you see that we've divided into web server A, B, and C. So for all intents and purposes, these three web servers are clones of each other, meaning they're identical. Now, the assumptions we need to make first is that all the requests have the same latency. Now, what is latency? Latency is the time it takes for the browser to fire a request and then get back a response from the server. That total travel time from when the browser starts making the request to when it receives a response is the latency. Now, for all intents and purposes, I'm going to pick an arbitrary number like 20 milliseconds. It really doesn't matter. The key thing here is that any browser making a request to the server and then getting back a response, this will always be 20 milliseconds. Not just the same browser, but all of the different browsers. They all have the same latency. This way, we even out any factors and we can easily better understand this example. The next assumption we need is that all servers have identical resources. So from the storage to the RAM, which is the memory, to the network, all of those resources we saw earlier, I want you to assume that all three of these web servers have the same amount. This way, we can see them as even clones. And by looking at them at even clones is how we can best understand this example. So here, what we want to talk about is when these requests start being made from the browser. Without a load balancer, we have no real way to figure out accurately how to properly manage the actual requests coming in. It's very easy to see where maybe all of these requests are going to one server. The reason why is because nothing is in the middle managing the actual request frequency and the actual load itself. So the load being the number of requests being made. Here, web server A is clearly getting overwhelmed. In another example here, yeah, we've split it a little bit, but clearly web server A is still on fire because it can easily be overloaded by the number of responses. If it gets a disproportionately large number of responses, then automatically we can see how a server can go down because it cannot handle the amount of traffic or load that it is receiving. This is where in comes the load balancer. The load balancer's sole purpose is to evenly distribute the actual load of requests between the servers available. Now again, under our assumptions where latency is the same, then of course we need to evenly split the load. In real life, different requests take different times. As we know, some requests might be larger because you're requesting more data or different data, or the latency might take longer because you have different network speeds, different computer speeds, different resources on your actual device. These are all possibilities. So what happens with a regular load balancer though? Well, again, a load balancer acts as the entry point into the application space or the system. Here, we're not going to communicate directly to the servers. Instead, we're going to communicate from the browser to the load balancer. That's the first thing that we're going to hit. And then the load balancer is going to distribute the actual requests themselves. So here, a very typical strategy for how to actually distribute the load is called round robin. Now, there are numerous ways that we can distribute load, and we'll talk about that later. Right now, that's not important. The main thing you need to understand about how the load balancer chooses what server to route a request to is the strategy, and the round robin strategy is a very common one. All this says is that we're just going to go in order of the list of servers we have access to. So, as requests come in, you'll just see that all it does is it goes to the next corresponding server in the list. So if we get a request, server A, then server B, then C, then A, then B, then C, then A, then B, then C, and in that order as long as requests come in. In real life, this might not be the most accurate representation, but what is really happening here is that you are, in theory, getting a really balanced load because our assumption is that the latency is the same between requests, which means that if we evenly distribute these requests, then all these servers should be sharing the load equally, meaning that the load balancer has accurately done what it's supposed to do. Now here, one thing you might notice is that, let's say, for example, we start doing this balancing act. In real life, what happens is that servers might go down. This is a very real possibility of what happens. The load balancer is smart enough to know that if a server goes down, it's not going to route any requests to it. Instead, it's just going to distribute the load with the remaining servers that are up. So this is another thing that the load balancer can do. The whole idea you can think about the load balancer is that it's essentially the traffic cop. It's the thing that knows where to send all the traffic. So it is the one that is responsible for balancing the traffic that's coming in. Load balancers are a very crucial component in system design. In many systems at scale, there are numerous load balancers because, as we see, if we get massive amounts of traffic, which most of these large systems do, then you need to be able to properly distribute this load so that your system is reliable. You want your servers to be evenly receiving the amount of requests so that these servers are not overwhelmed, because that is the whole point, really, of system design. Or at least it's one of the very crucial things that we're trying to maintain. We're trying to manage traffic, which is the whole idea of designing a system so that it's scalable. Of course, you want the system to solve the intended purpose of the application, but more importantly, you want to make sure that this system is robust and reliable. It should not go down from a large amount of traffic. So that's what you're designing around. So the load balancer is a very crucial component that really reflects some of these ideas that we're trying to solve in our system design. Now we're going to continue learning about other functionalities of these load balancers, and we're going to do a much deeper dive later in the course on a load balancer section where we talk about different strategies. But for now, we just need to understand again the high level of what these tools are, walking through the architecture of an application in a system. So this is a very general idea of what load balancers do. In the next video, let's keep going. I'll see you there.